Hi, most welcome to Dr. Acharya Academy. Today I'll discuss on the topic periodic trends with respect to atomic and ionic radius. This topic has been taken from NCERT Chemistry Class 11 book. This is the part number 1, unit number 3. Today's class number is 056. There are numerous physical properties of elements such as melting and boiling points, heat of fusions, vaporization, energy of atomization, etc. which show periodic variation. Here we will discuss about atomic and ionic radius, ionization enthalpy, electron gain enthalpy, and electronegativity. Next, number of class I am going to discuss. In this class number 056, I will discuss only about the periodic trends with respect to atomic and ionic radius. Just to imagine the size of an atom, the radius of this atom for measuring is so much complicated. It is not the simple like measuring the radius of a ball. Do you know why? Because first of all, the size of the atom, that means its radius, is 1.2 angstrom, and it is very, very small. And secondly, that this atom, if you consider that it is surrounded by electron cloud, that means nucleus in atom surrounded by the electron clouds, it doesn't have any sharp boundary like a ball, and that's why the determination of the atomic size cannot be precise. There is no practical way by which the size of an individual atom can be measured. But an estimate of the atomic size can be made by knowing the distance between atoms in the combined state. One practical approach to estimate the size of an atom for a non-metallic element like chlorine, it is to measure the distance between two atoms when they are bound together by a single bond in a covalent molecule, and from this value the covalent radius of the element can be calculated. Now I'll give one example in respect of the chlorine molecule. This is the chlorine atom, two atoms. This is a diatomic molecule, and two chlorine atoms is covalently singly bond, and covalently it attached to each other. So this distance, this bond distance is 198. So picometer. So half of the distance, 198 picometer by 2, that means 99 picometer. And it is taken as the atomic radius of chlorine. And this is the case for non-metals. What will happen for metals? Because metal will not form this type of diatomic molecule. So in this case, for metals, we'll call the metallic radius, and which is taken as half the internuclear distance separating the metal core in the metallic crystals. So these all are metallic crystals. So the distance between two adjacent copper atoms, as for example in a solid copper, is 256 picometer. You can see this is one atom, this is one atom, metal atom. And in this case, consider these are the copper atoms. So what is the internuclear distance? Here nucleus is there for this atom, this copper atom, and this for copper atom nucleus is there. So this internuclear distance divided by 2, and that will be the metallic radius. So this internuclear distance between the two adjacent copper atoms in solid copper is 256 picometer, and in this case the metallic radius 256 picometer divided by 2, and it will be 128 picometer. So we understand that for non-metallic elements covalent radius, and for metals it is a metallic radius. For simplicity, we'll use the term atomic radius for both cases. Atomic radius can be measured by X-ray or other spectroscopic methods. The atomic radius of a few elements is listed in the next table. I'll show you. Two trends are obvious. We can explain these trends in terms of nuclear charge and energy level. This is the table, and this period number 2, if you consider the atoms lithium, barium, boron, carbon, nitrogen, oxygen, and fluorine atoms, and atomic radius also reduced for lithium. Atomic radius is 152, and slowly along the period, this period number 2, it decreased atomic radius, and finally for the fluorine atom, atomic radius is 64. And similarly for the period number 3, here is the sodium, magnesium, aluminum, silicon, phosphorus, sulfur, and chlorine, and the atomic radius for sodium, that means the extreme left side, group number 1's sodium, its atomic radius is 186, and gradually it will decrease, and finally extreme right side halogen molecules atom is there chlorine, and it is the 99. All are in picometer. And if you consider in the group, then for group number 1, atomic radius will increase. That means least atomic radius is for the lithium, and for slowly it will increase the atomic radius for sodium, potassium, etc. In this way you can see. And you can see from the lithium, the atomic radius is 152. For sodium, its atomic radius is 186, and slowly it will increase down the group. And for the atoms of the elements belonging to the group number 17, this also you can see the atomic radius is increasing down the group. For fluorine atoms, it is a 64, for chlorine 99, and slowly it is increased along the group. And now you see that if you consider the period from the discussion in the unit number 2, we know during the electronic configuration determinations that along the period, outer shell will remain same, but due to the increase of the atomic number, the nuclear charge will be increased along the elements belonging to the period. And this results in the increasing attraction of electrons to the nucleus. See the periodic table. For alkali metals and halogens, alkali metals, this group number 1, and halogen, you know, group number 17. As you descend the group, that means here also you are descending down, coming down along the group for both cases, then what the principal quantum number n increases, we know. You can see here for lithium 2s1, that means 2 means it is the principal quantum number. For sodium, electronic configuration outer shells is the 3s1, 3 means it is the principal quantum number. During the discussion of the electronic configuration, it is already discussed in that class. Similarly, for group 17 also it is like that. For the period number 2, outer shell, whose principal quantum is 2, and this chlorine, if you go down, that means period number 3, then the outer shells, what is the principal quantum? It is 3. And group wise, if you come down, then principal quantum number increases and the valence shells are further from the nucleus. Principal number increases means it is attached to the more shell, outer shell, number is increasing, that means the valence electron will be added further from the nucleus. That means the shell having the principal quantum number 3, it has more distance than the shell which have the principal quantum number 2. That means the valence electrons is far away comparatively down the group from the nucleus, and this happens because the inner energy levels are filled with electrons which serve to shield the outer electrons from the pull of the nucleus. The shielding effect for the inner energy levels I already discussed in the unit number 2. That class you can read, you can learn, then it will be very clear for you. And for this reason, the size of the atom increases as reflected in the atomic radius. Note that the atomic radius of noble gas are not considered here, because the thing is that these noble gas all are monoatomic gas. That means for helium it is He, not He2. Being monoatomic, the noble gas non-bonded radius value are very large. In fact, radius of noble gas should be compared not with the covalent radius but with the van der Waals radius of other elements. And you can see in this card some atomic radius. This is the period number 2, you know, lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine. And if you put the card atomic radius in picometer versus the atomic number, then you can see that from the lithium, atomic radius is decreasing. And this is the along the group. From the previous discussion, we know that along the group, if you come down, then atomic radius is increased. So from here also in this curve, you can see in respect of atomic number increase from lithium, atomic radius increase for sodium, and then again atomic radius increase for potassium, and so on. And group number 17, first element is the fluorine. So from fluorine also down the group, chlorine, bromine, and iodine, that atomic radius is increased. So now here you understand the variation of atomic radius with atomic number across the period as well as across the group. Now I'll discuss about the ionic radius. We know the removal of an electron from an atom results in the formation of a cation, whereas the gain of an electron leads to an anion. The ionic radius can be estimated by measuring the distance between cations and anions in ionic crystals. In general, the ionic radius of elements exhibits the same trend as the atomic radius. Cation is smaller than its parent atom because it has fewer electrons while its nuclear charge remains the same. That means from the atom, if you remove the electron, then only cation will be formed. That means nuclear charge will remain same in ions, that means in cations, like the atoms, but number of electrons reduced. So what will happen? That electrons will feel more nuclear charge in this case for this cation, and the size, and in that case the cation size will be smaller. That is the reason. But for the size of an anion, for the anion, that means you are adding electron, and it will be larger than the parent ion because the addition of one or more electrons would result in increased repulsion among the electrons. Because whatever atoms, the number of electrons is there, for anions, more number of electrons is entered in the same outer shell, and in this case the increased repulsion among the electrons will happen and a decrease in effective nuclear charge. Effective nuclear charge also will be decreased because number of electrons increased. So number of electrons increased means per electron the effective nuclear charge will be decreased. These 2 points, the size of anions will be larger than that of the parent atom. Example, the ionic radius of fluid ion is 136 picometer. Fluid ion, whereas the atomic radius of the fluid is only 64 picometer. That means fluid ion is the anionic form of fluorine. Then as per this discussion, that size of the anion will be increased, and in this case the ionic radius is 136 picometer. When the atomic radius of fluorine atoms, it is only 64 picometer. Now we will take one example for cation. Sodium. Sodium cation. If it is sodium cation, its ionic radius is 95 picometer for Na+. Then this will be shorter than the atomic radius of sodium. And in this case also, in this example also, you see the atomic radius of sodium is 186. And the sodium's cation, as per this discussion, a cation is smaller than its parent ion. That means the ionic radius is of only 95 picometer for sodium ion. When we find some atoms and ions which contain the same number of electrons, we call them isoelectronic species. For example, of the isoelectric species are the O2 minus, F minus, Na plus, and Mg2 plus. For these 4 species, they have the same number of electrons, and their radius would be different because of their different nuclear charge. Though they have the same number of electrons, but we know that these atoms all have different atomic numbers. That means the different nuclear charge. The cation with the greater positive charge will have a smaller radius because of the greater attraction of the electrons to the nucleus. Anion with the greater negative charge will have the larger radius. In this case, the net repulsion of the electrons will outweigh the nuclear charge and the ion will expand in size. Now we consider one problem. That means in exam it may come that which of the following species will have the largest and smallest size? Mg, Mg2 plus, Al, Al3 plus. So we know that atomic radius decrease across a period. So cations are smaller than their parent ion. So if you consider these two, Mg and Mg2 plus, then obviously the Mg2 plus, this cation has less ionic radius than the atomic radius of the Mg atom. And among isoelectronic species, the one with the larger positive nuclear charge will have a smaller radius. In this case, you see Al3 plus. So it has larger positive nuclear charge than Mg2 plus. So hence what will happen? The largest species is Mg and the smallest one is Al3 plus. So you have to consider these two things, that cations are smaller than their parent ion, and we have to consider also isoelectronic species. In that case, the larger positive nuclear charge will have a smaller radius. So that's why Al3 plus is the smallest and Mg is the largest species. I hope that you understood what is the periodicity of the atomic radius and ionic radius for the elements along the period and along the group. I also create one podcast in the same name, Dr. Acharya Academy, for honors degree chemistry level education. You can go through this to get the more knowledge about the chemistry. Thank you so much for watching this class.